Simón Piga will talk about hypergraphs Turán problem.
Yes, please.
Maybe.
Yeah.
Yeah.
So yeah, this is not exactly the title that I gave before, but it's close enough. So yeah, many of the results that I will talk about are with other co-authors but different, so I will specify in a case. And so I'm gonna talk mainly about this hypergraph with quasi-random links, but I also will introduce the more common variants of this original Turán problem, and yeah, try to see how everything fits together in some story. So first of all, we are going to talk about k graphs. So those are k uniform hypergraphs. That means that the edges have k vertices, and the main parameter of this talk is going to be the Turán density, which is defined by this extremal number divided by the possible number of edges. So here, this extremal number is the maximum number of edges that you can have without containing a copy of f. So again, extremal number or n vertices for a hypergraph f is just the maximum number of edges that you can have in an n vertex graph without containing a copy of f. And this guy, you can normalize it by the maximum possible number of edges to get some density, and you take the limit, and this gives you a nice clean parameter between 0 and 1, which is the parameter that we want to study. Right? And for graphs, we have Erdős-Stone theorem, which determined this problem more or less completely. So the Turán density for graphs is very well known. And this is kind of one of the big achievements of combinatorics, is being able to determine this parameter for all graphs. There are many other results about the Turán densities and even the extremal numbers, so we know stability, and yeah, there are only few open questions in Turán problems for graphs. But what about for hypergraphs? So as you probably know, and if you don't know, you should reconsider your priorities probably. If you probably know, this Turán density is very hard for 3 uniform hypergraphs, even if you go to k equals 3, right? So you just forget about graphs, you take k uniform hypergraph, forget about k uniform hypergraph, you take only 3 uniform hypergraphs, and not even some formula for everything, but just one guy. So the Turán density of k4 is still a very complicated problem. Is open since the 40s. And even allegedly simpler if you take k4, the complete graph from 4 vertices minus 1 edge, so 4 vertices and 3 edges. This is also like a very, very hard problem. But yeah, the good part is that there are some Turán densities that we do know. Yeah? So this, I don't expect that everybody knows this, but we know some Turán densities. For example, the Turán density of this guy. So 5 vertices and these 3 edges. This we know that the Turán density is 2/9, and this was proven in the 70s by Golovash. If you are more fancy, for example, this guy, you can consider the Fano plane as a hypergraph as well, and there we have that the Turán density of this guy is 3/4, so we know that result. More recently, well, another guy that you can study is cycles. So cycles are also very normal or very typical hypergraph. So this is a cycle in 5 vertices, meaning that you have 5 vertices cyclically, and you connect every 3 consecutive edges, every 3 consecutive vertices. And yeah, this Turán density for C5 itself we don't know. For 5 vertices we don't know exactly, but recently, or relatively recently, it was proven that the Turán density of a sufficiently large cycle is 2 times square root of 3 minus 3, so some fairly irrational number. And the reason of this irrational number is because, so here the constructions are nice, the extremal constructions, but here this extremal construction is some kind of iterative construction that repeats itself, and of course if it is finite it never can achieve this number, but it tends to this number, it converges to this number. So the proof of this result was really need to consider these infinite kinds of examples. So this is kind of a new, not only a new result, but a new kind of result in some sense. Like we are now able to determine these very strange numbers as Turán densities. This result was improved recently. So before this guy was in the thousands or something, but now they reduced it to 8. and getting C5 will still be very nice. And the same happens for C5, so more or less the same story. At the beginning they prove it for C5 for arbitrarily for some large length of the cycle, but now they prove it for even C5 itself. And here C5 minus means again the same cycle as we have before, but you remove one edge. So it's like a smaller object. And interestingly, here this 1/4 looks much simpler, but again the 1/4 construction is achieved by some infinite construction again, right? So this guy is actually never really achieved, right? Infinitely many steps. So again, like some more classical results and some more new things, but there are many guys that we know in between, so many specific hypergraphs that we know in between, but still we are very far away from our knowledge for graphs that we have like a general formula, right? So we know a bit some spots here and there, but still the general formula is very far away from get there. So since this problem, again, even for 3 graphs is so hard, we can study variations of this problem to get it to see whether it gets simpler, right? And again, here most of the time I'm going to talk about 3 graphs, right? So everything going to be about 3 graphs. So 2 main things that I think you probably know. So if you have a 3 uniform hypergraph and you take 2 vertices, the codegree of these 2 vertices is going to be just the number of edges that contain this pair. So for example, in this case, the codegree is 4. And the minimum codegree is going to be, among all possible pairs, what is the minimum codegree that is achieved. So this construction, for example, has minimum codegree n/3 minus 1. Right? So the first variation that one can consider is the codegree Turán density, which is very similar to the previous one. So you take the extremal number, but now the extremal number 2, which is the minimum codegree possible, the maximum possible codegree that you can have without containing a copy of it. So here, before it was just number of edges, now is the minimum codegree. So just as an example, this construction has minimum codegree n/3 minus 1. Right? We just discussed this. And if you like try to prove it, it's easy to see that this guy does not contain a cycle on 5 vertices, right? So these 2 statements together, it means that the codegree Turán density of the cycle with 5 vertices is at least 1/3. So the Turán density would look for the best possible construction which has these characteristics, right? Like minimum codegree. And actually, this is the believed extremal example for C5. The other variation is a bit more subtle. So the other variation is quasi-randomness. And here, let me kind of informally define what would be the quasi-random Turán density. So the Turán density of a hypergraph F, the quasi-random Turán density of a hypergraph F, it's not a limit anymore, it's a supremum, but supremums and limiters are very, very close together. So it's the supremum of all possible densities, such that for every error term and a sufficiently large F-free graph, that's the maximum density that you can achieve. So let me write it in words, maybe it's a bit easier. So the quasi-random Turán density will be the maximum quasi-random density that you can have, that you still can have an F-free graph which is quasi-random with that density. So here it's more difficult to do it with limits because you have this error term. So you have to say, for every possible error term in my quasi-randomness, there is still a contract sample which has that density and still can contain copies of F. Right? So I know this is like a very strange object to grasp, but at the beginning when this idea came through, the reasoning was because there is a famous paper by Chung, Graham, and Wilson that proves that if you define this object for graphs, then the Turán density of every graph is always 0. So this means that if you have a sufficiently large quasi-random graph, then it will contain all fixed size subgraph inside. Right? So since your original graph is quasi-random, then everything will be inside basically. And then they in the same discussion they prove that this phenomena does not happen for hypergraphs. So there are some quasi-random hypergraphs which forbid still some graphs inside, some hypergraphs inside. And this new phenomena, people believe, maybe that's the reason why this problem is so hard for hypergraphs. So compared with graphs. So maybe for graphs this problem is very easy because all constructions which are meaningful are kind of very structured and not quasi-random, while for graphs you can have very quasi-random structures which are still able to forbid your graphs, your hypergraphs. The other thing that I should mention is that here, of course, quasi-randomness for hypergraphs, I haven't defined what quasi-randomness means, and it's like whatever you believe or you feel it should mean, in the sense that quasi-random should be something that behaves as random, right? It's a deterministic object, but it behaves as the random graph, or the random hypergraph. So for graphs, this definition is not so ambiguous because, again, this paper of Chung, Graham, and Wilson, they prove that more or less, like any reasonable, sensible definition that you can get for quasi-random graph, it will give you more or less the same family of quasi-random graphs. While for hypergraph, this is not the case. So for hypergraph, there is a branch of different possible quasi-randomness, and all of them are kind of meaningful, and they are not comparable necessarily all the time. So some quasi-randomness are stronger than others, but some others are just incomparable between themselves. So just this discussion of quasi-randomness is much more rich in hypergraphs. So we can define many types of quasi-randomness. So let me go to the first, or the most natural, I would say, definition of quasi-randomness for 3 uniform hypergraphs. So we say a tree graph is 3 dot rho d dense, and here the 3 dot means the type of quasi-randomness that we are talking about. If for every 3 set of vertices, the number of edges that go across those 3 set of vertices is at least a d proportion of what you would expect, of the a d proportion of the maximum minus some small error term. Okay, so again, the quasi-random 3 dot density means that everywhere you look, there is always at least a d proportion of the edges everywhere. So let me give you one nice example of this. So imagine you have a set of vertices and you orient the pairs of vertices randomly. Okay. Now you can construct a hypergraph in which the oriented triangles are edges and the non-oriented triangles are non-edges. Okay. So this guy, if you take 3 set of vertices, you will find always 1/4 proportion of the triangles will be oriented. So this means that the hypergraph constructed in this way, which now for some reason my H there disappeared, but the hypergraph
both of those actually belong to the H there? Should both of those triangles actually?
Yeah, this is supposed to be a non-oriented triangle. Yeah. Sorry, a copy-paste error there. So yeah, this guy is a non-oriented triangle. So forgive your eyes. This is a non-oriented triangle. So again, like whenever you take 3 set of vertices, like in X, Y, Z there, 1/4 of the triangles there are going to be oriented, and therefore this guy is 3 dot rho 1/4 dense. And the error term you always assume is very small. But more interesting for our topic, if you take 4 vertices here, and you try to construct as many triangles as possible in this like local game, you will always find at most 2 oriented triangles there. And I hope now the picture is fine. So again, every 4 vertices will contain at most 2 edges. And this hypergraph here, the K4 minus, which was the complete hypergraph on 4 vertices, minus 1 edge, that guy contains 3 edges. So this construction with the random triangles does not contain any copy of K4 minus. Right? And this means that the Turán density for this quasi-randomness of K4 minus is at least 1/4 because of this example. Right? And actually now it's proven that this value is actually equals to 1/4. So this construction is optimal for this kind of quasi-random. Okay, are we happy with this? Any questions? No? Great. So this is kind of the big philosophical question here. Can we, so now we have a bit simplified versions of the original Turán problem. And the question is whether we can have a version of the Erdős-Stone theorem, which was the original theorem that we have. So for every graph, we have a formula for calculating the Turán density. Maybe now in this simplified universe, we have some kind of formula for this codegree or the 3-dot variant. So this is, well, so far we don't have such formulas yet. And I'm going to show you here 3 different approaches that we can take, or that people have taken to consider this issue, the issue of trying to get like a general statement for Erdős-Stone, for hypergraphs, at least for these 3 variations. So one approach, which I think is still the most popular one, is just you give me a nice hypergraph and I try to calculate its Turán density, and I hope that after doing this 10 times or 20 times, I actually get a general formula, like I can learn enough to get actually a general formula. So we have K4, K4 minus, cycle minus an edge, and so on, right? The other approach, that is the one that I will try to push in this talk, is that, well, we could study not only the 3-dot notion of quasi-randomness, but we can study other notions of quasi-randomness for hypergraphs. As I said before, the type of quasi-randomness in hypergraphs is like a rich topic. So there are many different types of quasi-randomness. And in particular, one can study stronger notions, which would make the problem a bit easier, right? Because you have like a more uniform distribution of edges. And the last one is the idea of considering, okay, I don't want to, it's kind of like an analogy to the first one, I don't want to study the Turán densities of some specific objects, but I want to see what are the numbers that can be achieved as Turán densities, and see how complicated is this set, and maybe looking at that set, we can try to go to the first goal, which is going for the Erdős-Stone theorem. And here I just warning you from when it comes, here it's very reasonable to also consider this a bit larger problem, which is not only consider Turán densities for single graphs, but you also can forbid a family of hypergraphs, not only one single hypergraph. So in this context, the problem gets a bit easier, and therefore it makes sense to consider it, right? So maybe this is again another moment to stop and ask questions, like ask whether you have questions.
In what sense the problem become easier for this last one?
Because I mean here this is finite family, so this is a larger set, right? It contains more things. But in some sense here in this problem, you only have to consider the family of possible contact samples, and then you take the family to be just the things that are forbidden in that example. Right? While here you have to kind of worry about the 2 bounds, because this is the Turán density is the best example, but also it means that after that density you always contain the copy. So this problem is much more subtle, I would say. So let me go through the approaches one by one. This one I will just talk at the end and very shortly, but let me go one by one. So first, Turán densities of some hypergraphs, like some beautiful hypergraphs that we can study. So these 2 guys are known now. This the codegree Turán density of K4 minus is 1/4, and the quasi-random Turán density of K4 minus is also 1/4. This is nice because we don't know the Turán densities of this guy. Sorry, the normal Turán density of this guy is not known. So the codegree and the quasi-randomness make actually the job a bit easier, so much that we now know these results. Right? But if you add one more edge, then we immediately don't know what is going on. So the codegree Turán density of K4 now is still unknown, and the quasi-random Turán density of K4 is also unknown. And these 2 are very hard problems to attack. So again, like we were in the previous one, we didn't even know this. Now we know this, but still just one step further seems to be very hard. Still some Turán densities are known, So for example, as I said before, the codegree Turán density of C5 is expected to be this, the extremal example. We couldn't show this, but we, together with Sangüesa, Matamala, and Schacht, we managed to prove that this is the extremal example for C10 at least. So if you take a longer cycle, this is actually the extremal example, and it's not so much longer. It's just in C10. For C5 and the quasi-random Turán density, we already know the number, and this is known already for some time. So yeah, this is like a very nice result. For cycle minus an edge, we also know the numbers. So this is with Sales and Schulke. We know that the Turán density minus an edge is 0. The cycle minus an edge is 0, and the quasi-random Turán density of cycle minus an edge is also 0.
So when you show it's this extremal example for C10, is it also extremal for infinitely many Cn?
Is extremal for all Cn's which are not divisible by 3,
Yes.
and larger than
I guess at
19
least
or
10.
something. Yeah.
Oh.
Yeah,
what
because
is it?
19. I
19,
think.
okay.
Yeah.
Right.
Yeah. Yeah, because for cycles divisible by 3,
Yeah.
they appear for free.
Yeah,
You
yeah,
don't
yeah.
need any. There is no construction there.
Simón, can I ask a question? So
Yeah.
also, what is there a relation between gamma and pi? Meaning gamma is always bigger than pi?
That was conjectured before, but Ander here could tell you that is not true. Right? Yeah,
Okay.
it's recently disproven. Yeah.
And with the 3 dots.
Oh, there's 3
But,
dots.
but
I mean,
gamma is always
Ah,
smaller or
gamma?
equal to pi. And
Yeah,
also
yeah,
3 dot is also always smaller or
Yeah.
equal.
That's not.
Because-
Yeah,
Three dots
these
is
two
all-
compare with pi.
I mean gamma,
Gamma-
and pi 3 dots. Gamma and pi. 3
Between
dots.
those two.
Yeah.
That's
Yeah,
the
that's
thing.
correct.
Yeah, in that case we have examples in both directions, so there is no general thing. But these Turán densities are always smaller than the original one.
Yeah, that's clear.
Yeah. So yeah, a bit more is known here, but still very far from an Erdős-Thom theorem here. So just let me mention this beautiful result by Ander, because here this theorem tells you that which kind of extremal it tells you a family of possible extremal constructions which are actually all possible extremal constructions in a sense. So it's very close to some Erdős-Thom theorem in philosophy at least, but here there is a supremum, right? So it's not that here there is a finite family of possible constructions. You always can take, if you want to check what is the Turán density, the 3-dot Turán density of F, you still in principle would need to check infinitely many possible constructions. But now the family, before it was all possible hypergraph, now it's just these palette constructions, which I'm not gonna enter in the details, but it's a much smaller family, it's a much nicer family. So if you study that family well enough, you will maybe be close to Erdős-Thom theorem. So this is not yet there, but it's like an important step in that direction. So here we restrict the family of possible contraexamples. And immediately it tells us that not immediately, but it creates new nice results. For example, now we know infinitely many points and infinitely many values that are Turán densities. And also this proof for K4 minus, which was very hard before, with this result it gets very easy. So this is an important step in this direction, and just want to argue that if we think in this idea of going to Erdős-Thom, this definitely is going to be in the way. Let me show you then the second approach, this idea of the strong quasi-randomness or stronger quasi-randomness. So this 3-dot density, or 3-dot quasi-random condition is known as the weak quasi-random condition because in a sense is the weakest that you can define. So this, I said before that there are many quasi-randomness that you can define for hypergraphs, and again you can maybe come up with some different strange quasi-randomness, but one can definitely organize the best studied quasi-randomness in a lattice, and one can say this quasi-randomness is stronger than this other. There will be one quasi-randomness which is the strongest of all, 1 would be the weakest of all, and this is precisely the weakest of all possible, of all well-studied quasi-randomness. So since this is a very weak condition, it's very natural to push it harder, right? To push further away from the quasi-randomness. So one can take like even more uniform distribution of edges. So this cherry, or like I will denote it with cherry, the cherry quasi-randomness is the strongest possible quasi-random condition in this lattice of possible quasi-randomness, for which the Turán density is not yet trivial. So it's not the strongest of all possible quasi-randomness. If you go one step further, then you recover this graph result, and then everything gets trivial. So this is kind of one step before this. And I want to tell you what is this quasi-randomness. So for that I need to define the link of a graph. So if you give me a vertex in a hypergraph H, in a 3-uniform hypergraph H, the link of that vertex are going to be the set of pairs such that together with the vertex form a hyper-edge. And so, for example, in blue here is the link of B. And the nice thing is that this link is now a graph, right? So for every vertex you can associate a graph, and that gives you a lot of information of the hypergraph. So the cherry density, you say that the hypergraph is cherry row dense if all the links of your hypergraph are rho d dense, but rho d dense as graphs, right? The graphs are dense now, except for maybe some exceptional guys that you don't care so much. So again, whenever you look a vertex, I have a picture for this. So whenever you look a vertex in a hypergraph H, and you take two vertex sets, the number of the edges in between in the link, they are a d proportion of all of them. So here we have like this very chaotic behavior, right? Like for every vertex, the link graph of that vertex, it looks very quasi-random. And it's easy to prove that this condition is much stronger than the previous one. It's actually like strange that these guys actually exist, right? Yeah.
Complete graph is.
Yeah, complete graph also satisfies this. Yeah. Yeah. It could exist in non-trivial way. So people have studied this Turán density for cherries, for the cherry quasi-randomness, and we know much more. So this is just from one paper, Ryle, Roder, and Schacht. And here they prove, first of all, they prove that the Turán density of K4, which is open for all the other cases, here is not only not open, but is 0. So this really tells you how much stronger this condition is, right? Like in the other one, you needed at least density 5/9 to get something, and in here already with 0, you get K4. More strangely, even, I would say, there are some cliques which have the same Turán density. So this equality here in 1/2, it means that there are hypergraphs which have cherry density 1/2 minus epsilon, so very close to 1/2 but not yet there, which don't contain K6. Right? But then you add this the epsilon that is missing, and not only contain K6, but you contain already K8. Right? So one increasement in the density gives you already many cliques. And the same in this jump, which is even larger, right? From K11, you jump to K16. Right? Which is kind of very awkward, strange behavior of this Turán density. But if you look at this picture, there is something missing, of course. So K5, K9, and K10 are awkwardly not there. And this we proved a few years ago with the same co-author, but now two younger mathematicians are added there. And we could prove that the Turán density of K5 is actually lies somewhere in between here. Not in 0, not in 1/2, but in 1/3. So the Turán density of K5 is somewhere here. So this is kind of a bitter, let me say something not so not bringing so much hope in this, because the idea is that this should be much easier to calculate than the previous Turán densities. but already this proof was extremely hard. So the jump here on difficulty is not clear that it's going to be so easy that we can get some Erdo stone or something like this. So this is still, even for one graph, it was very hard. So I would expect that a general formula for clicks, for example, would still be very hard to construct. So here we need to, this is a nice application of regularity lemma and translating the conditions from the regularized graph to, the quasi-random conditions you can carry out to the reduced hypergraph. So we have a few new results.
Simon.
Yeah.
So 16 is where it stops, or do they have like an infinite?
They have a general
size?
upper bound for this.
But the exact values are only known up to 16.
Yeah.
It's not like I don't know, from 23 to 32 also or something.
No, they, like these gaps are not increasing. It's just this is the last construction that we know. So the issue here is now the other side. We don't have too many constructions that we believe are optimal. Yeah. So one new step that we have done recently is to now prove the Turán density, extending this notion of quasi-random of quasi-randomness, but not only for 3 uniform hypergraphs, but for k uniform hypergraphs. And there we can say, so still it's a very strong condition, so it allows you to prove many more things that you cannot prove in the normal condition. But we only could move to one click. So the smallest click possible, which is not just an edge, we can determine the Turán density, and oddly enough, it depends on whether k is odd or not. So yeah, this cherry condition now we define again by these links. So if we say that a k uniform hypergraph is cherry dense, it means that almost all vertices have a quasi-random link in the strongest notion of quasi-randomness for that dimension. So the link here of a k uniform hypergraph will be a k minus 1 uniform hypergraph, and we assume the maximum quasi-randomness there.
Maximum quasi-randomness in k minus 1 link will be also cherry quasi-randomness or something else.
It is even stronger than the cherry quasi-randomness.
Oh.
Yeah. It is the so for example, for 4 uniform hypergraphs, you take a vertex v, and here we in the 3 uniform link, we will assume we will get the triangle density. And this triangle density means that if you take any 3 set of pairs like this, the number of edges among this set of pairs, so this is P, Q, and R, is at least a d proportion of the number of triangles in P, Q, and R, plus, minus an error 10, and to the 3. So yeah, the notion is not the most natural one, but it's just the strongest possible quasi-randomness that you can get for every, and this happens for every link.
And so this is what you were saying. If you require this notion in 3 uniform, then all densities are 0.
Yeah.
Because of regularity.
Yes. Yeah. So basically, in this notion, in the cherry, you have all the links contain every subgraph inside, and still the Turán densities are not 0. Right? You still can forbid stuff. So yeah, the second thing is we have now again for 3 uniform we have a general formula that allows us to. So given this is kind of this is a generalization of what was obtained before by Rai, Radan, and Schacht. So for every density that you give me, I can calculate the density of double the click of the double the size, and this will be given by 1 minus 2 over alpha. So in particular, this means already some bounds for K9 and K10, which were open. and it's still open because the bounds are not still there, but at least we could push back the best upper bound. But let me try to convince you that I think the nicest thing we have is we obtained simpler proofs for the previous results. So we were able, because in this idea of pushing to the Erdős stone, this cherry condition should be simple enough to actually recover an Erdős stone theorem. So something that I believe is very important is to find proofs which are very simple. My co-authors, which are like very in love with regularity lemma, they say well, regularity is the initial step of everything, but I think it's meaningful to have a regularity-free proof. So yeah, let me see whether I can show you. So remember from the slide before here, the Turán density of K4 is 0. So let me try to show you that the Turán density of K4 is 0. So the statement there, without using regularity. And yeah, this proof is kind of nice and simple and cute, I would say. So you give me a hypergraph which is cherry rho d dense with density, any density larger than 0, so with any constant, and I need to prove that it contains K4. So, and remember this cherry rho d dense means that it can almost all links are quasirandom. So we start, and I'm very proud of my latex pictures, so I want you to contemplate them. So first you start with a vertex, and as I said before, because of this Chung, Graham, and Wilson, you contain every graph inside your link. In particular, you contain an arbitrarily large clique. So you take a clique of size t, with t is much larger than everything else, except n, but t is larger than all the constants. You actually can blow up this result, and you can actually find not only one copy of kt, but you can find many copies of kt. So a positive proportion of the possible kts are actually kts. And again, all the constants get worse, but in spirit, this statement is still the same. So just by a double counting argument, for every vertex, you have many copies. That means that there is one copy that is good for many vertices. Right? And here many means linearly many. And here I think is the nice, so the fact that this is in the link of all these vertices exactly means that all these edges are present, right? So for this pair here is in the link of all vertices here, that means that this vertex is connected to each and one of them. Then, but now this guy is a linear size set, so we can apply our condition. So that means that every vertex here has to have some dense link inside here, right? I mean, we have to get rid of the guys which doesn't have dense links, but we just ignore them. There are very only few of them. So every vertex in this KT contains a dense link in this part. And since we take T so much larger than D, and here the density is D, that means that there are two guys which share one edge in the other side. So this edge is in the link of these two. And if you concentrate enough, this is a copy of K4. So all possible edges are there. All four possible edges are there. Yeah. So this is a nice proof. Now, we have to generalize this proof in three ways somehow. So first, we need to generalize it for larger cliques. And this was already an obstacle. So trying to generalize this mirroring idea, so you generalize a large clique here, and then you copy it here, and so on. The first idea that you would have doesn't really work immediately. So you have to push a little bit harder. But yeah, I won't have time to go too much into the details. But it's also a nice generalization for doubling this argument. And then after you double the argument, we were able to find this general formula somehow. So that was yet another generalization. And the last step is finding for higher uniformities, not only for 3 uniform hypergraphs, but also for k uniform hypergraphs. And that again was much harder, so we only could do it for the first click. We cannot reproduce this kind of mirror argument as in here. Okay. So now let me finish with possible Turán densities. So this is a nice also approach to this problem. So the observation is that if you remember the Erdős stone for graphs and you consider the set of possible Turán densities, then this set looks very nice and very boring in a sense. It's just a set of dots in the interval 0, 1. They approach to 1, and yeah, this is all the story that we can say. So one maybe can try to say something about the Turán densities of this, the possible Turán densities for 3 uniform. And there we know some points there. The 2/9 is there, 1/4. This strange irrational number is also there. So one can say, maybe the behavior of these guys also have these like big gaps in between, right? So here there is a smaller gap, but still there is some gaps in between. So the behavior of the set is relatively more or less the same. And the hint for this, or why people believe this, is because Erdős proved long ago that here there is a gap. So here there are no Turán densities that can lie in here. So your Turán density is either 0 or 2/9, but cannot be in between. So maybe, and from here and there, I mean, from here on, we didn't know what happened. And it was a hope, I guess, that that could be possible, so that we have like these orange forbidden lines. But Frankel and Rödl in the 80s, they show that this is not the case. So they show that there is a point, this point, 48/49, but also infinitely many other points, for which there is no orange set in front. So there is no gap in front of it, right? So it's an accumulation point from the right. So this is a crashing problem, right? Like it means that the hope from before is not really true. Here, the one caveat is that they prove it for these finite families. So they didn't prove it for just single hypergraph. But if you study the set of Turán densities when you allow forbidding finitely many hypergraphs, then you get this result. But recently, I mean, let me just say that Picurco also later he was able to generalize this result in much more like deepness. So he is actually showing that this set has some nasty behavior. It's definitely not boring as the first one, and everything that you could expect could happen somehow. Like there are accumulation points from both sides, and yeah, it's a very messy set. And again, for finite families of hypergraphs. And these have been generalized recently for also for single hypergraphs and so on. But I don't want to go so much into the details of what is proven and what is not. But there are also new results not for finite families, but also for single graphs. And the set seems to behave also very strangely.
But do you know if there are accumulation points of the accumulation points?
I mean, I would say that Picurco also implies this.
Okay.
Yeah.
So could there be anything transcendental?
This is a big question. It's not known whether there is a transcendental number here. Yeah, it's an open question.
Wow.
Is the known irrational numbers except of this one?
Yeah, they are irrational numbers. Yes. I'm not sure if there are infinitely many. Are there infinitely many irrational numbers? There are infinitely many irrational
Yeah,
numbers.
in fact, there's like arbitrarily high algebraic degree. It's not just even quadratic.
Yeah. So yeah, this set is very complicated. It has very complicated properties.
Wait, what is the meaning of that white dot and that blue cross?
I was trying. It's just not so important, but I was trying to say that this set means that there's accumulation points from here, and this means that there is an accumulation point from the other side.
So So
There
it's
is
there.
not so
From
sorry.
left, right?
From the left, yes.
But this point is not this 2 square root 3.
No. I mean, no, don't allow me to go into many details in this thing. I just have to say this is very complicated and there are many accumulation points and the behavior is very strange.
So could it be possible that everything between 2 9 and 1 is actually a Turán density of something?
No, there is
No.
still more gaps in between.
There are known gaps in between. But also, I mean, you cannot expect a fully continuous thing here because the set of finite families is not.
Ah, I see.
But you can something that one can expect is an interval for which the Turán densities are dense in that interval, right? And that's still not known. But this orange guy, I mean, it's known that there are other orange jumps in here.
Up to 1 or up to some point?
No, up to something.
Up to some.
Yeah, there is no. It's also open whether they go arbitrarily large. Yeah. So this is a complicated issue, as you can see. So let me go to the first variant, which is so the codegree was called gamma. So this big gamma is the possible codegree Turán densities. And here the story is like we also know only a few cases. And the first question is whether we can have the hope that Erdos had before. So there is a blank spot at the beginning. So meaning that there is some epsilon here for which there are no Turán densities there. And recently also, or not so recently, we proved that no matter the epsilon, you always will find some Turán density in between. So in other words, there is an accumulation point even in 0 in this case. And this result was also generalized. I barely generalized it for many other cases. So there are infinitely many accumulation points from the left also in this way. So this is when you consider the gamma, the purest gamma somehow, the gamma which is possible Turán densities for one forbidden one hypergraph. If you go one step further and say, if you allow yourself to consider the set in which you forbid families, as I said before, the problem gets easier. And there you can prove actually that this set is dense in the interval. So all rational, every rational is a Turán density for in this case. So somehow how I think of this is that the problem becomes simpler from above somehow. So now the structure is there is so many good points in there that it's like kind of simpler again, right? So for the
no known irrational points.
not to my knowledge, but there might be some irrational points. For the 3 dot, for the 3 dot there was also some hope that maybe this was very complicated, but here this is simple, and the reasoning was because there is a gap again, and you can prove a gap at the beginning, so maybe now really there are gaps in this 3 dot density, in this 3 quasi-randomness. But again, I don't want to enter so much in the details, but if you go into the finite families, you can transfer many of the properties that you get in the normal Turán density, of the properties of the sets of possible Turán densities, you can transfer them to the set of possible 3 dot densities. So the hope that this set was somehow simpler than this one are, I think, not there anymore. Yeah, this set is very, very complicated again. So something that has not been studied, and I would be very interested in study, is what happened with the cherry density here. Because I think I have a slide for this, yes. So what is a set of possible cherry densities? So far we are in the step 0 in this case. So we know that there are these 3 points there, but we don't know any lower we don't know whether 0 is an accumulation point. And there is, on the one hand, one could believe that this is a quasi-random Turán density, so it should behave as this Turán density. So very messy, very complicated. There might be many gaps and many accumulation points and so on. But if you believe on Anders' palette theorem, which is not proven for this cherry density yet, but it could be true still for this cherry density. So if you believe in that palette theorem, then this cherry density, it behaves as a codegree for these palette constructions somehow. So on the one hand, it's a quasi-random construction, so one might expect some very very complicated behavior, like very dense and accumulation points and so on, and also some jumps and gaps. As I said before, like there are here many clicks that accumulate here, right? Like so, and here there is like from 11 to 16, they all accumulate here. So it feels that this will have like a very jumpy behavior. There will be big steps in between. But on the other hand, we know that this thing behaves as a codegree in this regularized world, in the reduced hypergraph. So one can expect the behavior of the codegree, which is everything is a Turán density. Right? So some days I wake up thinking everything is a Turán density. Some other days I wake up thinking, no, actually it accumulates in some points. So I think kind of it's a very, sincerely a very interesting question what happens here. Also, and this is kind of the philosophy of this talk, one question that I would like now in this like philosophical moment maybe, I would ask whether there is other Turán densities, other notions of Turán density which we can explore, for which there is a meaningful and non-trivial Erdos-Stone theorem. Right? So one can go, we went to the largest possible quasi-randomness for which the Turán density is not trivial, and we get that this problem is still very complicated, so can we go further in some like out-of-the-box notion of quasi-randomness, or maybe, yeah, other notions. For example, there is this positive codegree that is also have been studied, and it might be that there are jumps there, or also one can combine, what if you combine the quasi-random condition with the 3 dots, so the classical quasi-random condition, you combine it with a codegree condition that also is a meaningful problem, and we don't know the behavior of these things, how they interact. And it would be interesting knowing whether, like, in some point when you explore these very new things, you can get something like an Erdos-Stone theorem there. So let me finish with 2 questions. One question is about what I was saying before, the difference between the finite and the infinite. Sorry, the finite and the single. So this guy is the possible Turán densities for single graphs, and this is for finite families, and it's not known whether this is actually different or not. So when you forbid only one hypergraph, it's not clear whether you obtain more possible points when you forbid more hypergraphs. And this is not known for any of the variations. So in any case, would be, I think, an interesting topic. And a different question, which is also related with this, would be whether this Turán density, so for 3 uniform codegree, generalize this result that says the whole interval, that all the rationals are Turán densities, but not, so it's known for finite families, but it's not known for single hypergraphs. So we know that doing this is much more work than that, so I would be very curious whether, not only whether it's true or not, but also how to prove it. Right? It would be like a big important step in that direction. So this, I think, is more or less it. I want to finish with someone very wise who told me that these Turán problems are important, so I think we all have to pay attention to him.
Thank you. We should have asked him for the hypergraph case.
Yeah, he was not available. So he didn't have enough time, I think.
This is found somewhere or AI generated?
So it was interesting, the talk the other day, that this is AI generated, but I couldn't manage to the AI to give me the formula. So I think that I had to like paste it on top somehow. Because the other day the guy was saying that the AI goes in different tracks, right? So to generate images, I think is not the same intelligence that to generate formulas. Right? So it was very stupid to do this.
So can you go back to the slide of your behavior? Yeah, so in here, why your first theorem, the Turán density
they varies in depend on the character of the inequality.
Mhm.
So that's my question. Why this happen?
So in this, when k is even, you can find an algebraic construction that only works when k is multiple of 2. You can find a construction that has density exactly 1/2 and gives you forbids the first clicks somehow. There is a parity issue basically, like in a triangle, right? In a graph, the problem is a parity.
So for the three uniform hypergraphs, how well do we understand which three uniform hypergraphs have like quasi-random density, either the 3 dot or the cherry, equal to 0?
So we understand very well for 3 uniform. So for 3
Okay.
uniform hypergraphs,
Yeah.
there is a characterization which which tells you which 3 uniform hypergraphs have Turán density 0 in this
Oh,
quasi-random
yeah.
variation. So
Yeah.
there is a full characterization there. But it's not generalized. We cannot generalize it for k uniform.
Okay.
Only for 3 uniform. It's a
And this is for
nice and simple characterization.
well, I guess like these two that you discussed, the 3 dot and the cherries.
No, it only applies to 3 dot. For the
Okay.
cherry, we don't know it.
Cherry we don't know, okay.
And there are some suspicious, but it's already kind of complicated to wrap your head around it. It's not so easy characterization.
Okay.
But we don't know, the result is not there yet.
Yeah, so you mentioned that when you have the cherry condition, then you get that almost every link is quasi-random.
Mhm.
Do you have examples where like these two notions are meaningfully different? So every link is quasi-random, or only almost every? Like if you would have another threshold, like pi cherry bar or something, that says just every link is quasi-random, then would they be the same, or would they?
My suspicion is that they are the same.
But
Because in the regularized world, it looks the same.
right. But you haven't proved.
No. But I mean, I would say for Turán problems, it should be the same.
Any other questions?
So if we apply a hypergraph regulator map in this setting, then the typical strategy is considering the reduced hypergraph. And this reduced hypergraph also maintaining this cherry quasi-randomness. So this reduced hypergraph also.
So the reduced hypergraph this condition translates into the reduced hypergraph in a like very natural way.
So either maintain the quasi-randomness, right?
No, I mean it's not that the reduced hypergraph is quasi-random itself,
Okay.
but it satisfies some kind of codegree condition. So that's so if you know regularity, like the triads that you have there, whenever you fix 2 of this set of pairs, they will have a substantial amount of neighbors in the front, and substantial depending on this d. I don't have it here, but you will have a d proportion of all possible neighbors.
Any other questions? Okay, if not, let's thank the speaker.